Hello, my name is Nathaniel. Today we are now going to do question 3 of step 3 2020. So we are now going to do something called complex numbers. Well, complex numbers, again, I'm going to reiterate this introduction many times. Complex numbers are not any more real than real numbers because they are also as real as real numbers. So they are on the form a plus ib or r e to the power of I theta, depending on who you're asking. Well, the a plus ib is known as the Cartesian or rectangular form, while re I theta is known as the polar form. So we are now going to use a mixture of Cartesian and polar forms. So the point GAB is defined to be the centroid of the triangle ABK. So well, that means k minus a equals to d minus a e to the power of negative I pi over 3. Remember, and you multiply, in this is positive, in the exponent, the imaginary part of the exponent is positive. That means you're dealing with an anti-clockwise rotation. So this means that GAB equals to 1/3 a plus b plus a plus b minus a e to the power negative I pi over 3, which, and you go do the math, which is a 2 minus e to the power of negative I pi over 3 over 3, and plus b 1 plus e to the power negative I pi over 3 over 3. So, and you actually go find the rectangular forms for this, which we're not going to do. So 2 minus e to the power negative I pi over 3 over 3. Actually, we are going to find the rectangular forms. So e to the power negative I pi over 3 equals to half minus square root 3 over 2i. 2 minus root 3 over half minus root 3 over 2i over 3 is equal to 1 over 3 minus, wait, did I do it right? 2 minus half over 3 is equal to half minus, 2 minus square root 3 over 2 over 3, 2 minus square root 2 plus square root 3 over 2 over 3i, which you go calculate happily equals 1 over the square root 3 of omega. So what omega is? Omega is the 12th root of unity. Well, everything's confusing. Now, those tau fanatics, as they are called, will use tau as a substitute on pi. And they're not wrong. Their arguments are not wrong. However, pi is dealing with area and tau is dealing with perimeter, and tau will arguably be a more interesting unit to use. Half minus square root 3 over 2i over 3 is equal to half plus 2 plus square root 3 over 2i over 3. Did I get that right? Yeah, I definitely. Plus square root 3 plus square root 3 over 2i over 3. As you can see here, the imaginary parts are negative on each other. That's why we call it the omega conjugate. And the conjugate is basically a reflection around the real axis. So that means the conjugate of a plus ib is a minus ib. So we are basically done. So GAB is 1 over the omega a plus omega star b. And it's called omega star because the mathematician said, hey, let's put a star, and then we're going to use this as a conjugate. Haha, just kidding. But anyway, mathematical notation is a really confusing and interesting subject and you want to go into it. But now we are not. So the quadrilateral Q1 has vertices A, B, C, D, and the quadrilateral Q2 has vertices GAB, GBC, GCD, GDA in that order. So we're now going to find GAB equals to 1 over square root 3 omega a plus omega star b, and GBC equals to 1 over the square root of 3 omega b plus omega star c. GCD is equal to 1 over the square root of 3 omega c plus omega star d, and GDA equals to 1 over the square root of 3 omega d plus omega star a. Got that right. Now, a parallelogram. What defines a parallelogram? Well, in Euclidean R-squared geometry, as it is called, the modulus, the length of the two parallel sides are the same. So we are going to define four numbers, vectors or complex numbers by a, b, c, and d. So this means that c minus b equals to d minus a, and b minus a equals to d. C minus D. Isn't it wonderful, these two identities? So we are going to find G, BC minus G, AB it's called, equals to 1 over the square root of 3 omega b plus omega star c minus omega star b minus omega a, which to the switching identities, as I happily call it, they are equal to 1 over the square root of 3 omega c minus d plus omega star d minus a. Isn't it wonderful? And this exactly equals to GCD minus GDA. Perfect. So we have just proved that it is a parallelogram, and one can apply the same argument to the other two sides. But since we have already proved that it's a parallelogram, it's a parallelogram. So we're going to discuss why this is an equilateral triangle. Now these are 12 roots on unity, so that means we can visualize them as a flattened star, you call it that. This is omega, this is omega, omega star, negative omega star. And omega, so we are going to find BC minus AB, the GBC minus GAB. It was 1 over square root 3 omega B minus A plus omega star C minus B. And GCA minus GBC is equal to 1 over square root 3 omega C minus B plus omega star A minus C. So if we can, so we had just seen, so so GAB minus GCA, we're just going to put all three expressions up here just for double checking, plus omega star B minus A. So we are going to figure out how to cancel omega star C minus B and omega C minus B. So if you can rotate this from omega star, you get omega, and if you get omega, you get omega star B minus A, and if you get omega A minus C, you can rotate it to get omega star A minus C, which just shows that the 3 points or 3 distances, you will call it, are in an equilateral triangle, because you can rotate it 120 degrees or pi over 3 radians. You will get, no, not pi over 3 radians, tau over 3 radians. You know, yeah, I know, this is very, very, very confusing. Right, so you see, the equilateral triangle, the definition is that you can rotate any of the 3 points. It has a dihedral group on order 6, you call it that, or dihedral group of, yeah, the group order is 6 or 3, depending on who you're asking again. So anyway, so what are we going to discuss here? So an equilateral triangle basically has 3 points, and you can rotate 120 degrees and still get the same equilateral triangle. And this symmetry has just shown that the points GAB, GBC, and GCA both form an equilateral triangle. And in addition to this, there's another identity which I'm not quite sure on the name of, is that you trisect all the angles of any triangle and then find their intersection points, you will get another equilateral triangle. Well, that's enough triangles for today, I suppose, and see you in another step video.